Okay, the next thing I'd like to talk about is the Gibbs-Duhem equation, and I'm probably pronouncing that name incorrectly. Gibbs-Duhem equation. Okay, so we have for our binary mixture that the Gibbs energy is the number of moles times the chemical potential of species A plus the number of moles of B times the chemical potential of species B. Now, if we want to calculate dG from this, let's assume that we can't assume that any of these are constant. Okay, so we're going to have to use the product rule on both of these terms. Okay, so applying the product rule to each term, we get something that looks like this. Now, we've also seen earlier in this section that if we hold pressure and temperature constant, dG is equal to mu A dNA plus mu B dNB. All right, so if we compare these two equations, so we equate these, then that means at constant temperature and pressure, this term will cancel with this term on the other side, and this term will cancel with this term on the other side, and that leaves me with these two terms. So what I'm left with is Na d mu A plus Nb d mu B, and on the other side, everything canceled, so that's equal to 0. Okay, so this is for two species, but we can write it in a more general case for any number of species, and you can see the pattern allows us to write it using some summation notation. And that would look something like this. It's the sum over J of Nj d mu J. That's the left-hand side. And the right-hand side is equal to 0. And so this is the Gibbs-Duhem equation. Okay, so this equation tells us something important. It tells us that we can't change the chemical potential of one component without changing the chemical potential of another component. So going back to the binary case, you can see if the chemical potential of A goes down, then the chemical potential of B must go up in order to maintain this sum equaling 0. So let me take this binary formula and let me solve it for one of these changes in chemical potential. I'll solve it for d mu B. So d mu B is equal to the negative of Na over Nb times d mu A. And since Na and Nb are both moles, then that means that those numbers are always positive. And so that means that d mu A and d mu B always have opposite signs. Okay. Okay, so let me show you an example of this. Let's say I have a binary mixture with Na having twice as many moles as Nb. And let's say that mu A changes by 1 joule per mole, then what's delta mu B? Okay, so this is a straightforward application of the formula that I just wrote down. I'll write it down again. Instead of using differentials, I'll use deltas, since we're talking about a finite change instead of an infinitesimal one. So delta mu b is equal to negative NA over NB, delta mu A. And since NA was twice as large as NB, then this is minus 2 delta mu A. And delta mu A was 1 joule per mole, so this is minus 2 joules per mole. So notice that because there was half as much B as A, then B must change twice as much as A. In order to counterbalance and keep the sum equal to 0 in the Gibbs-Duhem equation. All right, and the Gibbs-Duhem equation holds for any partial molar quantity, not just the partial molar Gibbs energy, aka chemical potential, but for any partial molar quantity, which is the topic of this section. So for example, I can do the Gibbs-Duhem equation for the partial molar volumes. So the sum of Nj times, now instead of d mu, I'm going to do dV, where this is the partial molar volume. Partial molar volume. And that must equal 0. And so this means for a binary mixture, dVB is equal to minus NA over NB dVB. So I'm just rearranging the equation that has two terms, A and B, in this sum, just like I did before for the chemical potential. All right, so let's take a look at the how we can see this using some experimental data. Okay, so I've drawn this graph. This is figure 5a.1 in your textbook. And this is a graph of the partial molar volumes, Vj, in a water ethanol mixture as we change the composition. So the x-axis is the mole fraction of ethanol. So it's increasing as we go to the right. So as we go to the right, we're adding more ethanol. And since these mole fractions have to add to 1, since these are the only two components, then they must add to 100, add up to 100% of the mixture. So these add to 1, and that means as Xe increases this way, XH2O is decreasing this way, or another way of thinking of it is H2O molar fraction increases from right to left, and the ethanol molar fraction increases from left to right. Okay, so we see what happens here is I have a steep drop, and this is the ethanol molar volume. I have a steep drop in the ethanol molar volume. That's going to cause a rise in the H2O molar volume, as expected, because we have this negative sign. If one increases, the other decreases. Also, if we look at, let me write the equation for ethanol and water here off to the side. So I'm just rewriting this equation right here, where B is going to be H2O and A is going to be ethanol. Okay. So VH2O increased, so that's positive. Therefore, dVe is going to be negative. It's going to decrease. And let's look at this coefficient out front. This is the number of moles of ethanol over the number of moles of H2O. So in this region of the graph over here on the left, there is not very much ethanol, and there's a lot of water. So that means that Ne over NH2O, this coefficient here, is small, because Ne is much smaller than NH2O over here on the left. And so we see that this small coefficient means that it means that a large change in dVe, so as we see here, we have a steep drop, multiplied by a small number is going to be a small increase in VH2O. And I probably should have made this a little flatter. I think I made it a little too steep. Okay, so a large change causes a small change here because of this coefficient. And now let's look at over here on the right-hand side. Okay, so now here we have a lot of ethanol and not as much water. So Ne on this side, Ne over NH2O is large amount of ethanol compared to water. And so here, a small change in VE multiplied by a large number will cause a large change in VH2O. And we see that here. VE starts to flatten out. So the change in VE is getting smaller and smaller, but the change in VH2O is getting steeper and steeper. Okay, so let's talk a little bit more about the thermodynamics of mixing. So for a binary mixture, we've already seen that G can be written mu A Na plus mu B Nb. And we know that G tends to decrease. And we talked about that in the last chapter. And in particular, we talked about how dG less than 0 is a spontaneous change. And a experimental observation is that if we mix two gases in a container, the mixing of those gases is spontaneous. So putting all this together, that must mean that G must decrease when you mix two gases. Okay, so let's investigate that. Okay, I changed the lighting a little bit because that shadow was starting to bother me. So let's mix two perfect gases. So we have n moles of gas A, we have n moles of gas B, and they're both at the same temperature and pressure. And we mix them together. Okay, so going way back to chapter 3E, we had an expression for the molar Gibbs energy as a function of pressure, okay? And that's equal to the standard, so 1 bar molar Gibbs energy for that substance, so this is a constant, plus RT ln P over P standard. And again, P standard is 1 bar. So before we mix, that means we have pure gas A and pure gas B. And we've discussed before that the molar Gibbs energy of a pure substance is equal to its chemical potential. So to begin with, each of these substances is going to obey this equation because they're both pure substances to begin with before mixing. Now, to simplify notation a little bit, since P standard is 1 bar, then we will replace this quantity with a dimensionless quantity, and we'll just understand that it's unitless as long as pressure is in bars, and this unitless number is telling us how many bars of pressure we have. So let me write that out real quick. Okay, so since P standard is 1 bar, we'll write P over P standard as just P, which is a unitless number, as long as we're using bars for P. Okay, so we're turning this into a unitless number as long as we measure pressure in bars. Okay, so this simplifies the notation a little bit. Now we can write mu equals mu standard plus RT ln P. Okay, so let's calculate the Gibbs energy before mixing. So before mixing, I'm going to have some initial Gibbs energy, and I'm using this equation that I just wrote down above. And for these mu's, I'm going to use this equation because right now the mu's are pure substances, so I can use this equation. So mu A becomes mu A standard. Again, that's a constant. Plus RT ln P. Both gases are at pressure P to begin with. Remember I said that earlier, that they're both starting at the same temperature and pressure. And then the second term is just the same thing, but now with mu B. And that's the Gibbs energy before mixing. All right, how about after mixing? All right, after mixing, we're going to have a final pressure that's equal to the sum of the partial pressures of the two components of our mixed gas. So PA and PB are the partial pressures of the two gases. So these partial pressures are the new pressures of each gas after mixing. The new pressures of the two gases. Okay, so let's put that in our formula. So Na mu A plus RT ln PA. So the only thing that changed here was the pressure. Temperature, we're assuming the temperature stays the same. Plus NB mu B plus RT ln PB. All right, so now I want to subtract these. I want to find delta G, which is going to be G final minus G initial. So before I flip the page, let's just take a look at this. You see, if I subtract this formula from this one, the Na mu A standard term is going to cancel, the NB mu B standard and NB mu B standard, those are going to cancel when I subtract. And then I'll be left with these two terms that have NARTLN in front of either a P or a PA, and then these two terms, NBRTLN and NBRTLN. Okay, so let's put all that together. Okay, so here we go. The delta G that we get from mixing, GF minus G initial, we're left with these two terms. It looks like there's no subtraction here, but remember that there was, and what I did is I just combined that by making it in the denominator, putting it in the denominator of the natural log. Okay, so there was a subtraction here. This was ln PA minus ln P. This was ln PB minus ln P. Okay, so I'm going to rewrite these N, this NA and this NB using this formula. So this just says that if I take the mole fraction times the total number of moles, that'll give me the number of moles of that substance. So if J makes up 1/2 of the moles, I take 1/2 times the total number of moles of everything combined, and I will get the number of moles of J. So I'm going to make those substitutions up here. I'm also going to do something similar for the P's. So we can also write P J equals XJP. So we've seen this before when we were talking about partial pressures back in chapter 1. And let me rearrange that. If I divide both sides by P, I get PJ over P is equal to XJ. And so you can see right away that's going to go right here and right here. So this is going to end up being X. This is actually XA, and this is actually XB. All right, so making all these changes, we get this simpler formula. So the NA became XJN, so it became XAN. So there's my XA. The N I factored out because I also got an N over here when I converted NB into XBN. So the N factored out. And I'm left with XA ln XA plus XB ln XB inside. All right, so this is the Gibbs mixing, the change in Gibbs when you're mixing perfect gases. And something to note here is that these x's are fractions, right? Fractions of a whole. So xj is less than 1 always, because something cannot make up more than 100% of the total. And so if that's true, then ln of something less than 1 is negative. So these natural logs are negative. Natural log of the xj. Which means that this is a negative number, this is a negative number, these are all positive numbers. That means that delta mix G is less than 0. And so this is what we have already observed experimentally. We've shown that it is that it must be true, that we've confirmed that perfect gases mix spontaneously.